Hey guys, welcome to my YouTube channel. So in this lecture we are going to continue our semiconductor series lecture. So up to last class we have done all the prerequisites, like what is mean by semiconductor, what is n-type, what is mean by p-type, and what is the charge distribution over different concepts like uniformly distributed, non-uniformly distributed, and then charge neutrality. Everything we have covered to the very good extent. That is an IIT standard, like that kind of thing that we have gone through, very depth and very detailed concepts that we have gone through. So I think that will be very much helpful for you guys to find the fundamentals in the core, because fundamentals is very much important. So far we have seen some 15 to 20 lectures, right? So that all the things will come here. So far we see the very important term, that is a Fermi-Dirac distribution. So many of the engineering students who are completed EC triple may not know what is the term. Even some staffs may not know the exact definition, how to explain it. But here I will make it very simple, that many guys may know once you guys have already studied semiconductor physics or EDC. This is a function of Fermi-Dirac distribution. That what the thing that it will say is that it is the function that f of E is depending on energy levels. Okay, so this energy level which is related to some this formula. So from this one you guys may not understand what the thing is. Let me give you one of the simplest explanation. What the thing is that it gives what's the function gives is it's give the probability of having electrons. It's give probability of having electrons. It's in simple term, or probability of occupying any energy levels, or probability of or what we can say is the probability of occupancy of any energy levels at any temperature T by electrons. So important term is the electrons. So the same thing that what they are ideally representing is for, especially for electron. So here they given the terms of probability, so that will come into picture. So the functional value will be equal to 0 or greater than will be, or greater max to 1. So this is probability, right? So as you guys know, so in this term that we can say what are the different things. This f of E is nothing but Fermi energy level. The Fermi energy level that last class we discussed, right? So this is the uppermost energy level, where below which every energy level is filled with electron. So that extension is the Fermi-Dirac distribution. So last class we see just the definition of EF. Now they are giving some probabilistic distributive function. So E is the any energy level that having that is the E is the energy level at which we are trying to calculate the presence of electron. So you guys know, right? So last class we have saw one band structure. So EF is EFN, EFP, like that way we see, right? So up to that only that is the max level where the electrons will be available. Below which all the electrons available, above which no electrons will be available. So using that we are making sure in the particular energy level E what is the probability of presence of electron. So that is what this Fermi-Dirac distribution will be able to explain it. So let's go deeper dive into it. So we know that f of E is the probability of finding electron, right? So then what is mean by 1 minus f of E? Then that will be the probability of finding holes in the valence band. So f of E, which is nothing but the probability of finding. So this is nothing but probability of, I am making simply probability of finding electrons. So probability of finding electrons at any energy level. At any energy level E. If 1 minus f of E, then what it will stay? It is reverse of it. So it may be what we can say probability of not having any electron at any energy level, or simply what we can say, which is nothing but the probability of finding holes. The exact opposite version, right? So in probability we find, right? So similar to that, the probability of finding holes in valence band. Okay. So let's take some cases like what are the approximate graph. This is distributive function, right? So if we can draw one distributive graph also. So here we can state this as a variation of f of E with the temperature. So variation in f of E the Fermi-Dirac distributive function with temperature. So if we vary the temperature, how the Dirac distributive functions will take place. So first case, let's take T which is equal to 0 Kelvin. Okay. So in that subsession, let's take A where E is greater than EF. So this is the condition where we are taking the energy level which is above Fermi-Dirac Fermi energy level of that particular function. Which means what will happen? There will be more probability of the presence of electron. We are taking that only. Okay. So E is greater than that. So if we apply in f of E, then what we can state is that 1 divided by 1 plus e power e minus e of f. So we will state a function that e minus e of f only, right? So there will be some positive term divided by 0 because of 0 Kelvin. So that one we have used. So 1 by 0 which is equal to infinity. So e per infinity, right? So e per infinity is also infinity. So 1 by infinity which will also be equal to, which is equal to 0. Okay, so this is the case. So let's take the second case. So where this is the energy level which is less than EF. So in this case what see, we have took the example energy level that is above EF. So let me draw a simple diagram so that you guys can able to understand it clearly. So this is a conduction band, valence band, and this is some EF that we are having. Let's take an example that this is the EF. Okay. So this is EC lower band and EC is upper band and this is EF. So if we take any energy level at this state, then what will happen? This is the condition here. So this is the condition that is here. So what is this? E is greater than EF. So if we take any condition below which, so that is what this B condition that we are using. So this is E is greater than EF and here E is less than EF. So clearly we can say the probability of presence of electron will be 0 here, but the probability of presence of electron is 10% because there will be presence of electron here. So that is what we are coming into picture. So f of E which will be equal to 1 divided by 1 plus which is greater quantity. So it will be negative max. So minus greater divided by 0. So which will be e power minus 0, right? So e power minus infinity is 0. So that will be 1 by 1 which is equal to 1. So probability of presence of electron below the Fermi energy level is 10%. So there will be there will be a presence of electron. So that is what they are trying to say. So let's take the C part. So where E which is equal to EF. So what will happen? F of E which will be equal to 1 divided by, this is 0. So 1 plus E per 0. So which is equal to 1 by 2. So the probability of presence of electron at the Fermi level will be 50%. There may be electron, may not be electron. So the probability is depending on this one. So if we draw this distributive function, so we may get into a good observation here. That what will happen? So let's take this as E. So this is the center point, that is EF. So this is E is greater than EF and this is E less than EF. Okay, I hope it's understood. So this is the Fermi-Dirac distributive function. So f of E. So if it is less than graph, then the presence of electron here it will be for sure that is 1. So up to which EF that is 1. But at the EF it is 50%. So we may not know. So this is 1 here, this is 1 by 2 and this is 0. So okay. So above which it is 0, completely 0. So if we draw it, if we plot the graph, then this will exactly hit like this. Okay, then it will trace the boundary of 0. So I'm mentioning like this way. Okay, I hope it's understood for you guys. So this is for ideal one. So this is for ideal one. That is what the temperature T which is equal to 0 Kelvin. So it is ideal. But everything in this world cannot be ideal, right? So if the temperature increases or decreases, based on that, the graph will shift. So the temperature is divided by quantity, right? In the graph, if the formula, if you see, the it is divided by temperature. So KT. So if the temperature increases, then the value will quietly decrease. Okay. So according to that, if we make an observation, we already discussed, right? If the temperature is greater than 300 Kelvin, if the temperature is keep on increasing, the conductivity for sure will decrease. So from that observation, we can coming to picture that it will slightly will be reduced. But at this stage it will be 1 by 2 only. So that is fixed. So then it will slowly trace the boundary. So this is the condition where T is equal to 300 Kelvin. So if we further reduce the temperature, what will happen? then it will further reduces. So it will be further like this. Okay, so it will be, if the curve dips there, here it will be races outside. Okay, I hope it's understood. Let me draw in another curve. So this is the curve. So red color is the 400 degrees temperatures. So the amount decreased here will be increased here. So that's what we are mentioning here. So as the temperature increases, the conductivity slowly decreases, right? So that's what. So making the presence of electron below, which will be slightly decreased, because the energy electrons will be jumping into upper state as the temperature increases. So that's why the presence of electron will increases here. This region, the margin of increase is this margin of decrease, because these electrons are jumped and come here. So that's what we can say. If even further increases, then it will not be in our case. So we already see, right? So if we keep on increasing the temperature, then that is not the expected case. So far I think this is good for you guys to understand. So from next lecture, let's get more into density of states, and let's plot these graphs into even more understanding of these things. If you guys have any doubt, please ping in the comment section and stay tuned for the next lecture. I hope this I have explained it neatly. So this is one of the very good thing, the presence of electrons. I think you guys have got a very good explanation, I hope. So if you guys like the video, please share, like and subscribe. Thank you. Stay tuned.